Okay, today we'll discuss magnetic monopole charge is a topological charge. And my magnetic monopole charge, what was? Charge G was given by 4 pi by E. How did we find these monopoles? We found them by requiring certain boundary or asymptotic or special infinity behavior of the various fields. For example, finite energy, and these were finite energy solutions with the property that phi b times phi b goes to a square as a radial coordinate goes to infinity. The Higgs vacuum. So the scalar field at the spatial boundary is in the Higgs vacuum. And also covariant derivative of phi b goes to, let me write it in longhand first, d mu of phi minus E b c d a mu b phi d. This also goes to 0 as r goes to infinity. And these go to 0 faster than 1 by r. One by r goes to 0 at r infinity. They go faster than 1 by r. Why faster than 1 by r at r infinity? Because the Hamiltonian density contains square of this object, right? di phi b square, d0 phi b square. So boundary behavior of this object would be then faster than 1 by r square. And if I want to find out the energy contribution from the boundary terms, boundary behavior, the energy is 3 integral dx, d3x. d3x goes like r square, right? r square dr, d theta, d phi, right? And then sine theta. So for large r, that goes like r square. So if boundary does not contribute any energy, then these fields should have a behavior faster than 1 by r square r, so that the square of this is faster than 1 by r square, and you have an r square in the numerator. So some r is still left in the denominator. You take r going to infinity there, so there is no energy from the vacuum, asymptotic vacuum. So that's the reason you want it to be little faster than 1 by r. Now this property, the second property, well, all second property and the first property, these two properties together, these two properties imply that a mu b at asymptotic spatial infinity should behave like 1 by a square E a b c d phi c d mu phi d plus 1 by a phi b a mu as r goes to infinity for an arbitrary a mu. What does that mean? That means that the solution of this equation d mu phi goes to 0 as r goes to infinity is provided by a mu of this kind, where phi asymptotically behaves like this. Phi square is a square. Should I leave this as an exercise or should we do it? Check this. How would we check it? Let's plug this into this and check whether covariant derivative at spatial infinity is 0 or not. So d mu phi b, which is d mu phi b minus e epsilon b c d a mu c phi d, and that goes in d mu phi b e epsilon b b c d, and let's put this object here, 1 by a square e epsilon c e f phi e d mu phi f plus 1 by a phi c a mu that's times phi d, right? Have we done right? Everything right? Just plug this solution into this. Now, this is phi c phi d multiplying epsilon b c d, therefore it's 0. For any a, this small this a, so this term doesn't contribute because it is symmetric in phi c and phi d multiplied by an object which is antisymmetric in phi and c. Now, this is 2 epsilons here. You know the simple identity of product of 2 epsilon symbols? Something CEF. CF, FCE. Epsilon symbol doesn't change if I make a cyclic change of the indices. So I have written as FCE. C is the common one here. The product of these objects is d delta b d bf, this and this, and delta de minus be delta be delta df. The simple identity multiplying 2 epsilons with 1 common index. Use that here. This e and e cancels. We have a square times that object now. delta CF delta DE minus delta BE. What happened? Something is not right. This is BF, not CF. BF delta DF times FE d mu F phi F phi D. BF DE DE, so it is phi E d mu phi B. That's the first term. BF makes FB and DE makes these two minus BE, so phi B DF phi D d mu phi D. Now this object I can write as minus half phi B d mu of phi D phi D. This is phi D square. Phi D square asymptotically is A square. D mu of A square is 0. A is constant. So this term doesn't contribute. Phi E asymptotically is A square. That kills this A square. This is same as this. Clear? So this is, you can say, the most general solution of this condition. Well, the most general is that this is the possible. See, one way of seeing is that any vector phi B, I can resolve it along an internal space vector phi B and orthogonal to it. This is the component that I call along it. This is the orthogonal to it. Right? Now I could have called this by a different name, and in order to solve it, you will discover that in order to solve it, this has to be d mu, and this is A mu is arbitrary. Clear? So now let me construct an object. Define a field strength through field strength F mu nu, no B internal space index, through the field strength of this gauge theory as equal to 1 by A phi B F mu nu. I can always do that, because all this tells me is that this F mu nu that I have written here is 1 by A is A by phi B call it phi b, phi c of f mu nu c. That's what it is. And this object, for r going to infinity, this object is a. So it is phi c by a f mu nu c. So this f mu nu that we have constructed asymptotically is phi c times f mu nu non-abelian divided by the vacuum expectation value A. And now if I put this A into it, which means construct the non-abelian f mu nu from this A, is he sleeping? Huh? Construct f mu nu from here. We have the gauge potential given in this form. I can construct the corresponding f mu nu non-abelian field strength. Put that in it here and see what this object looks like. So f mu nu asymptotically, this f mu nu that I have constructed, r going to infinity, is 1 e by a cube phi b d mu phi c epsilon b c d b c phi d plus d mu a mu d mu a mu. Just do this small exercise. Use this. Let's call it 1. In here, if I construct the f mu nu, I have to take an antisymmetric derivative of these objects. Okay. So d nu here, d nu antisymmetrized will not give me anything. D nu here will give me a term like the one I have written here. And similarly, from the second term, I will get term like this. And remember, this is phi c by a here. So if I multiply by phi c here, so this will make it phi square by a asymptotically, that is 1. Huh? So I have this. Then there are the cross terms in non-abelian field strength, nonlinear terms, right? 2a terms. You take the product of 2a terms that also has a structure of the same kind. So that will add up to this, and with the result that you will get a right coefficient here. Okay. And as it is, notice that it is antisymmetric in mu and nu. Why it's antisymmetric in mu and nu? Because it's antisymmetric in C and D. So this is the form of this f so constructed. You could define it everywhere, but at the boundary this is the property it has. You could, I mean, this was a definition everywhere, this one. But at the boundary it has this structure. Now this is a small exercise, but there is a little bigger exercise. the f mu nu so constructed, f mu nu so constructed satisfies the equations d mu of f mu nu equal to 0, d mu of f mu nu dual equal to 0 as r goes to infinity. Is that clear? If the original f mu nu A satisfied, if f mu nu A satisfies the original equations, f mu nu A and pi, right, the full Yang-Mills equations that we had in V phi going to 0 limit, lambda going to 0 and Prasad-Sommerfeld limit. You can check it. It's supposed to be true otherwise also, but you can check it in the Prasad-Sommerfeld limit, that f mu nu and phi satisfy the original equations. If they satisfy original equations, then this f so constructed satisfies this. Now these are the equations of motion of a U1 theory. So what you have is, you have asymptotically these fields satisfying equations of motions of a electromagnetic theory, Maxwell's theory. This U1 is the one that is in the original. This is the one that survives after spontaneous symmetry breaking in the vacuum, boundary vacuum. Is that something of the construction that is there? Now, recall the non-abelian magnetic field Bi was written in terms of field strength as minus half epsilon I j k FB jk. Which, from what we have done already here, r going to infinity, has the following structure. I'll write it: minus 1 by 2 A4 epsilon I j k epsilon C df phi b phi c dj phi d dk phi f minus 1 by a epsilon I j k phi b dj ak. This is exactly the exercise I have put in there, is that calculate Fijk here, this, and then contract it with phi c and a to get this answer. This is the same thing, the Ij component of the same equation. And let me, if I calculate phi b of bi from here and give that a name bi, just give it a name and calculate it from here. So if I contract phi b with phi b here, I think I have missed something. I have missed an e here. If I contract this phi b with this phi b, that gives me phi b square, which is asymptotically a square. That kills this a square. So asymptotically it is minus 2a square epsilon I j k epsilon c df phi c dj phi d dk phi f minus phi b square is a square divided by a, so I have an a epsilon I j k dj dk at r going to infinity. And this is up. If I lower it down, it just simply changes the sign. This something is not right. Something is not right. Something is not right. Something is not right. Did I do everything right? Yes, I did not do everything right, which is that phi b, this let's call it a times b. Give it a name a times b. Then this will become cube, and this is phi b. This is this a goes away, right? And I missed an e somewhere. E was everywhere, right? So now let's calculate the magnetic charge of this object from there, here. How was the magnetic charge defined? This is how we had defined magnetic charge. And I can rewrite this as d3x of ordinary derivative of phi b phi bi. Di, because covariant derivative on B is 0, Bianchi identity, because covariant derivative of B covariant divergence. Huh? M? M and also G, if you remember from, M was without this A, without this 1 by A, right? Because we discovered M is A times G. Now this I can write as A into a surface integral dSi of phi b at spatial infinity. So these fields have values at spatial infinity, and we have figured it out. What does it look like at spatial infinity? This object, or what exactly is there? There is B there, right? So this object is same as S what we call Bi there. This is a total divergence. So when I integrate this piece here, that will give me answer 0, because it will give me an answer on the boundary of S2, and S2 has no boundary, right? So the only term that will contribute is the first term. So therefore I can write it as the 1 by 2e S infinity square S2 at infinity dSi epsilon I j k epsilon b c d phi b hat d j phi c hat d k phi d hat, where I have introduced phi a hat to be phi a divided by a, and phi b divided by a. Because it's just in the integral of this term. 2e, a I have divided, a is a constant, divides all these three phi's, so make them into hat. This is a plus here. Is that? It's equal to that is, I've simply said substituted bi that I constructed from there.
This is just the second term. The bi is the second term.
From here I have gone to this because phi b bi is bi. Because that's the way we defined bi. That's how we defined this bi. This is definition of bi. So this integral, let's give it a name. We'll give it a name, 4 pi by e times t. Now t is 1 by 8 pi dSi of epsilon I j k epsilon b c d phi b dj phi c k phi hat d. Now this T is a topological charge. T is a topological charge. To see that, construct a current for which this would be a charge. In things, you take the time component of that current, integrated over 3x, that would be a charge. So we'll construct a current for which this object is a charge, a conserved current for, and the current is K mu is equal to 1 by 8 pi epsilon mu nu alpha beta epsilon b c d d nu phi b hat d alpha phi c hat d beta phi d hat. This is a current 1 by 8 pi mu nu alpha beta b c d nu phi hat b d alpha phi hat c. There is one free index mu here, that is the index that the current carries. This current has the property its flow divergence 0. Because if I hit by d mu, when it hits on d mu here, because of the antisymmetry of this object, everywhere, because of the antisymmetric symbol here, d mu k mu is 0 by construction, and d mu k mu is 0 without using any equation of motion. Without using any equation of motion. So therefore, it is a topological current. Topological conserved current.
This current has an opposite property than ordinary current under time reversal polarity.
And this T that we have constructed here, now one second, this current is also a total divergence. Because I can rewrite K mu as 1 by 8 pi d mu of epsilon mu nu alpha beta or let me no let sorry let me take the time component of this current. One by 8 pi epsilon I g k epsilon b c d d I phi b d j phi c d k phi d. This I can also write as 8 pi epsilon I j k epsilon b d di acting on phi b dj phi c dk phi d. Therefore, the charge d3x of k0 now it's a three divergence. So therefore I can write it as a surface integral. And that's precisely what we call T. Epsilon I j k, I forgot to write it, right? So what we've shown is that magnetic monopole charge is 4 pi divided by E times the topological charge. Now this topological charge, what kind of a topological property does it measure? Because a topological charge measures a topological property. What is the topological property that T measures? It measures how many times does the unit vector phi a of x go around the Higgs vacuum space The Higgs vacuum is defined by phi b times phi b equal to a square, and if I convert that into unit vectors, that defines this is a unit vector. So that's what the Higgs vacuum is, and topologically it is an S2 because this is an equation of an S2. So how many times phi goes around the Higgs vacuum space given by S2 as we go around the spatial infinity, as we go around spatial infinity S2. S2 at infinity. So these x coordinates at spatial infinity, ordinate space, I have an S2 described by two polar angles, let me call them theta phi, different from this phi. So as I span the space once in that S2 at spatial infinity, how many times do I go around the Higgs vacuum space S2? So it measures that number. So it measures what is called, it measures maps of S2 to S2. S2 to S2 is slightly more complicated to visualize, but S1 to S1 is very easy to visualize. S1 is a circle, S1, another S1 is a circle. If I go around this circle once, I can go around this circle. Maybe this whole circle is mapped to one point here, so I don't go around at all. So that is topologically trivial. But if I go around once here and I map every point of this at one point of this, so it is just 1 to 1. So that will measure, if I'm going around this circle once, this circle once, topological number 1. But I could map points of this in such a way that they go around this twice, right? Or 3 times or 4 times. So that will measure the winding of this object around this object twice, 3 times, 4 times. This is the concept that is generalized to S2. It can generalize to any Sn. So this is a mapping that gives you the maps of S2 to S2. And let me now give you an exercise. S2 to S2 maps described by phi Bx, and let me put a subscript n on it, where phi's are unit vectors in the internal space with phi b x n. This is n and this is x. They look same in my handwriting, or maybe let me call it m. M looks somewhat different. Given by the components cosine m phi sine theta sine m phi sine theta cosine theta, where theta and this phi are coordinates on two sphere at radial infinity. Now clearly this is a vector in internal space of length 1, because this square plus this square plus this square is 1. Clear? Now if I calculate this object T for this map, exercise is calculate T for this and show that it is M. let me write it explicitly. T is 1 by 8 pi d3x of epsilon BCD di phi c n dj phi hat d n dk. There's also an epsilon ijk here. Phi b c d n. So calculate this object for this answer. And show that that object is M. And clearly from the way I have given the answer, as I go for various values of theta phi in the spatial infinity S2, theta ranges from 0 to pi, phi azimuthal angle from 0 to 2 pi. So all the points of S2 would be covered by different values of this. So as I move around this, that will give me one cover. As I move from phi 0 to 2 pi, this combined angle will be will move from m times 0 to 2 pi, which means 0 to 2 pi m. So in the internal space, this is going to cover it m times. Clear? So let me now summarize what we have done. BPS monopole is a finite energy solution or finite energy solution or a soliton, because it carries this topological charge, with its magnetic field, magnetic charge given in terms of a topological charge T, magnetic charge G given into topological charge, characterizing maps of S2 to S2, and G is 4 pi by E T, with T as +1 and -1 for monopole and anti-monopole. So that completes the discussion of how do we see the magnetic charge of a monopole as a topological charge. So far we have discussed magnetic poles which have only magnetic charge and no electric charge. But we could also think of objects which have both electric charge and magnetic charge. Such objects are called dyons. So now let me start a discussion of dyons. These carry both magnetic and as well and electric charge. Now recall, to study zero electric charge configurations, solitons, we had put A0 B equal to 0. For zero electric charge solitons, A0 B was 8 s, and correspondingly the non-abelian electric field strength was 0. But if we want to give them electric charge, A0 cannot be 0 and electric field strength cannot be 0. For non-zero electric charge, solitons, let me take A0 to be A0B to be XB divided by ER square JAER. Parameterize my A0 component of the non-abelian gauge field by XB divided by ER square JAER. This is the JAER is the same dimensionless variable that we had introduced to study monopole. And all other ansatz we keep them the same. What were the other ansatz we had? Phi B was XB or RB. I have called it RB. RB and XB are the same. Sometimes I will write XB and sometimes RB. RB ER square HAER, and ABI was minus epsilon BIJ RJ ER square 1 minus K AER. So the only change is that instead of taking A0 to be 0, we parameterize it like this. As earlier, in the Higgs vacuum, phi b, that's what we have at r equal to infinity, is a square. And as usual, we define the magnetic charge by the definition G that I wrote just a little while ago, is same as or equivalently d3x of Bi covariant derivative phi b. These are the various definitions we used. And now similarly the electric charge is dSi s to infinity of the even electric field at the boundary, EI, the electric field, abelian electric field, from the abelian F mu nu that we constructed earlier. Which is F mu nu is 1 by A phi b F mu nu. And from this F mu nu you construct the corresponding E by taking the 0 I component, and that is what this is. Sorry, electric charge should be Q. So I can rewrite this as A dSi EBI phi b, where EBI is the constructed E from this field strength, and this can also be written as d3x of EBI covariant derivative of phi b. And these are our definitions of electric and magnetic charge. Remember, di EBI is 0 and di BBI is 0 by Bianchi identity. Now, if I were to write the mass of this such an object which has both electric and magnetic charge, we have worked out what the energy density is already, except that we now do not have to put E square term equal to 0 there. So, the energy or mass is d3x of half EBI plus BI plus DI phi I B DI phi I B plus D0 phi B D0 phi B plus if we want to keep V phi. If you want to go to Prasad Sommerfeld limit, we will drop V phi. So, these are all the terms that we had in the Hamiltonian. But now notice, and for the pure monopole we had dropped this and we had dropped this. Now look at this object D0 phi B is D0 phi B minus E times epsilon B C D of A0 B and phi A0 C phi D. This is what this covariant derivative is. We are interested in static configurations. So, static configurations makes it 0 because we are interested in static configurations. Now, look at A0 C and phi d ansatz. Both of them are proportional to RB. So this is proportional to RC and this is proportional to RD. So which means they have a structure epsilon BCD times RC times RD, symmetric in C and D, antisymmetric in C and D. So for the ansatz we have, this is also 0. So which means mass now is D3x half of EBI square plus half of BBI square plus half of D phi I square plus now we'll do a similar trick that we did earlier. Try to write these as sums of squares and in a particular fashion. One half EBI minus sine theta covariant derivative of phi b plus BBI minus cosine theta covariant derivative of phi b square now square of this has E square term, cosine square of this has B square term, square of this also has a sine square di phi term plus sine square plus cosine square d phi square term, that's this. But then there are additional terms which are cross terms. So we subtract them out. This is the cross term from here, sin theta EB d covariant derivative phi. Theta is a constant. We just introduce a theta in it. It's a constant. And this is the cross term here. Now this object is electric charge. This object is magnetic charge. This is a complete square. This is a complete square. And if you remember the form of V phi, that was a complete square. So these are positive quantities. Therefore, this M is bounded by slow. This is A times electric charge, right? Because 1 by A there. This is also A times magnetic charge. And now let's go to Prasad-Sommerfeld limit and see what this means. Prasad-Sommerfeld limit means V phi equal to 0 through lambda going to 0 then the minimum that potential is given by the Bogomolny equations. Now EB equal to sine theta covariant derivative of phi b and BBI cosine theta covariant derivative of phi b. This is the minimum of this square term and this square term. And for such a value, m is given by simply sine theta AQ plus cosine theta AG. But configurations which satisfy this also tell you because I still have it here, right? From here, if I calculate electric charge multiply this by maybe I'll leave this as an exercise. For configurations that satisfy this and this, tangent theta is given by Q by G. Multiply it by E and integrate it. That gives me E square integral equal to sine theta times Q. Multiply this by B, that gives integral B square. But integral E square plus B square is again mass. So that tells me that mass for this theory is A times G square plus Q square square root. Put sine theta in this, and that is same as mod of this complex quantity Q plus Ig. Is this exercise clear? Or do you want me to do it? So which means Bogomolny bound is saturated for these BPS dions. Now let me try to solve these equations, Bogomolny equations, solution of Bogomolny equations. We have 15 minutes, right? 5 minutes. Oh. I think we should try to be in time in the morning, see. Now just 10 minutes of work is getting left here because of this, we're starting a little late. In 10 minutes I could just give you the solution, or should I give it as an exercise? Alright, let me give it as an exercise in 5 minutes. For the ansatz that we wrote earlier, calculate the following objects, exercise. E times electric field Bk is equal to delta Bk minus Nb Nk divided by R square K times J plus Nb Nk divided by R square R J prime J. For pure monopole, J was 0, so this object was 0. So this is something new. These things are same things that we had earlier. Minus delta Bk minus Nb Nk divided by R square K prime minus Nb Nk divided by R square K square minus 1, and E covariant derivative K of phi b delta Bk minus Nb Nk divided by R square Hk plus Nb Nk divided by R square R H prime H. Incidentally, did you do this exercise for the monopole case? Did it work out? Anybody had any difficulty with? Huh? These things worked out? So this is the field strengths, electric and magnetic non-abelian field strengths, and this is the covariant derivative of phi for the ansatz that we wrote. And now let's use the Bogomolny equations. E Bi is sine theta di phi b, and B Bi is cosine theta covariant derivative phi b, and equate the coefficients. That gives us R K prime is equal to minus cosine theta Hk, and that is the same, this one. Bk is cosine times this, so this is this cosine times this, that is this equation. And then from here K square minus 1 is cosine times minus R H prime H, this times cosine times this, that is the second equation. Now the first equation is this and this to be equated with a sign here. So that is K, J is sine theta Hk, this and this, and this and this. R j prime j is sine theta R h prime h. These are the same old equations except that there is a cosine theta factor here, a constant. These are the new equations. Now look at this equation here. K is common, so this tells me this equation is only a differential form of this equation, because if you look at it, j times r this equation is simply, you can rewrite this as j divided by r, derivative with respect to r, sine theta h by r, derivative with respect to r. That is only a differential form of this equation, divided by r. Now the solution of these equations, introduced a parameter zeta hat, which is AER cosine theta, which is AER was the same old zeta we had introduced times cosine theta. And introduce a quantity A hat, which is cosine theta times h. Then do a little algebra with these things and convince yourself that k and h hat, so written, satisfy the same old equations that we had for the monopole case. In other words, exercise, show that zeta hat h zeta hat of d zeta hat is same as minus, sorry, this is d zeta k h hat zeta hat k zeta hat and k square zeta hat minus 1 is minus zeta hat dh hat zeta hat d zeta hat minus h. Now these are the same old equations except written in different variables. Therefore, solutions of this object is same as what we call k0 of zeta hat. K0 is the solution for the monopole, and h hat zeta hat is the monopole solution we wrote as a function of zeta hat. Therefore, h psi is h0 of psi cosine theta divided by cosine theta, k psi is k0 cosine theta, and j psi, from there we know what it is. J psi is h psi cosine theta times tan theta, and psi is AER, and h0 psi is psi cotangent hyperbolic psi minus 1, and k0 psi is psi sine hyperbolic psi. Okay, so I think we'll stop here. So now we have the solutions for diamond, and we also know how to calculate the electric and magnetic charges. And the next time now we'll discuss that quantum mechanically the electric and magnetic charges should live on a lattice. We'll try to understand Saha, Dirac, and Zwanziger-Schwinger condition in this context.